Okay, can you hear me? Yeah, thank you. Thank you to the organizers for inviting me. I'm giving a mostly review talk with something current and also some thoughts for the future that hopefully will inspire some discussions. Urosh gave the Cool Kids talk. So I'm going to talk about old perturbative theory. So this is based on several works that some of you may know. And we have a code, PyBird. There is also PyOwl, PyBird but nightly, available on request with a bispectrum. And PyFoul, the latest one, Python code for observables in weak lensing. You do a 2D projection, basically. Yeah. Beautiful. Okay, so yeah, I mean, giving a review talk, I thought about this nice painting that you know describes in a somewhat you know dreamlike way what's the story from the beginning to the end, with some desperation in between, some joy, and so on. So I guess this describes the journey. So what is this for? Like, why am I talking to you today? So we are getting a wait. Yes. We are getting a lot of large-scale structured data, as we all know and heard. What is the end goal of the experimental effort? So to me, the end goal is really understanding the universe. So practically then, it means that you have some model and you really want to measure known parameters. And in principle, you want to detect unknown physics. And the universe is unique in that, I mean, you can do this across a wide range of energy scales in principle. In practice, I mean, of course, as we know, this creates a lot of difficulties because, I mean, the observable, you cannot play with it. As with any experimental information, we struggle both for precision and the data will become more and more precise. And at some point, you really need accuracy. So accuracy is how close you are to the truth. Accuracy means from the data point of view, less and less systematics, and this now really becomes an experimental issue because, I mean, of course, if you lower the precision, if you have higher precision, lower statistical error, you want also much better accuracy. But also, from a theoretical point of view, you want a reliable interpretation of the data. And I argue that the effective theory large-scale structure gives just that. So it is an analytical understanding in terms of description of the system based on good effective theory. Sorry. In a nutshell, you all know what this is. So it is basically you identify your basic degree of freedom and symmetries. Basic degree of freedom is literally the cold dark matter density and momentum, or the displacement in LPT. Anyway, it is basically the fluctuations, ultimately imprinted by inflation. And the symmetries are translation, rotation, diffeomorphism, invariance. You identify your physical cutoff of the theory, okay? So there is a KNL, or sometimes called the KM, due to the, you know, scale of formation of halos. So it is a nonlinear scale of dark matter. So beyond that, delta is equal 1, you cannot perturbatively expand anymore. And also KR, which is something that we discovered along the way, that we should have known. But I mean, you can also get it out of measuring this coefficient, and this is like a scale where velocity dispersion becomes large. Okay, which of the two expansion parameters is larger? It really depends on the tracer. It depends on the observable. So the idea is that we do perturbation theory where possible, renormalize a known effect of small scales. So renormalization is something that comes just with the perturbative definition of the theory. It's not that something only quantum, and we resum a non-perturbative effect, which in this case, they are a large-scale IR displacement that, luckily being very large scales, you can describe reliably. And congratulations, now you have a beautiful theory of unobservable cold dark matter. Totally unobservable, not true, because I can use this for the weak lensing. And now you add the bias schema. You go to Ricci space in the case of galaxy clustering. You do projection integrals depending on what you measure, especially if you want to do weak lensing to get to specific observables. Now you can build the likelihood and compare to the data. The important thing is to estimate the scale cuts. Now, any perturbation theory has its own estimation of scale cuts, and I will discuss about them. Now, why the pain? Because, I mean, this is not simple. And the idea is that the contribution to the power spectrum set a different Kmax, okay, that you can use up to which you can accurately model your data. And the number of modes in large-scale structure scales as Kmax cube, whereas the CMB is beautiful, linear, very well understood, two-dimensional. So here there is a max square. And so this is like a very rough scaling of the previous generation and current generation surveys design Euclid with the number of modes compared to Planck and, well, CMBS4 that I didn't remove, I mean, but hopefully there will be something. And here there is a rough scaling about what you can use. You see the number of modes you can use if you stay within linear theory, if you go to one-loop theory, which is the current state of the art for the power spectrum, and this is the total, okay? So then, yeah, it seems that there is still something that we can gain. Still, I mean, this Kmax to the cube, I mean, is not a super small power. You can see that there may be diminishing returns. Now, what have we computed? We have computed delta 1, delta 2, delta 3, delta 4, almost delta 5, okay? Let me define the almost, so basically the bias schema has been computed, the normalization has been computed, and very recently Zvonimir, Rick, they have a paper discussing the normalization at fifth order. Why I put a red check? I consider it done when there is at least a second independent group and confirmation. Okay, but I mean, it's basically done, and Ricci space distortion are still missing. Okay, now you see, with this you can compute loop order at 3 level. Of course, the 2-point function, 3-point function, 4-point function, etc. They they are in this y-axis. And then at one loop order, you need cubic to go for one loop power spectrum, and you need fourth order to go to one loop by spectrum. You need fifth order for the two-loop power spectrum. Data at the moment measure only the power spectrum and by spectrum, okay? So, I mean, yeah, there is some attempt to get the 4-point function in real space. I mean, Oliver, for instance, has worked on that, but so far, basically, this is the situation where we are. Okay, let me then start by telling you more in detail where do we come from. So the story, and this was pre-COVID, so really it was a very long time ago. We started to apply the perturbative EFT at one loop power spectrum, using the one loop power spectrum to the previous generation of BOS data. So in fact, we were getting incredible constraints, and many people wouldn't believe this. So we did many validations. The paper is like 70 page long. Conservative scale count, I mean, by comparing to today. We found agreement with Planck. There were still some confusions, especially the low-ES, which wasn't our fault. It was the fault of the estimator. So overall, this looks, I mean, that's true. Overall, this looks like a good job. So, and at the time, people were wondering, will the full shape become the new standard analysis? Okay, so as you know, the kid here, no, we were very, I mean, optimistic. All the life was ahead of us. So this, I think, it was a very interesting moment in the story. There was this blinded PT challenge. So this group by Takada and Nishimichi, they made a huge volume, simulated volume, 10 boxes with the total volume 566 gigaparsec cube over H. And with a realistic HOD, and they gave us the data. And we were two independent groups in this paper, and then, I mean, also other group joined the challenge. And we agreed between us, and we agreed with the truth, okay? And so I think that this really helped establish the reliability of the method. Now, today, many codes are available for this one-loop power spectrum. So this is become really a standard analysis, okay? And in fact, it went into official collaboration. This is the DESI validation. It compared the Velociraptor, FOLPS, PyBird across different tracers, finding pretty good agreement. And that's it. Okay, now let me come to the first challenge, conceptual issue that I believe is solved. That's why I put in the past. So the crucial issue is where to stop the perturbative fit. There is a usual trade-off between accuracy and precision, that smaller scales have smaller error. Perturbative approach, though, starts to fail. And the interesting thing is that the theory is a controlled approximate description of reality, and so you are making a theoretical error if you compute in perturbation theory up to order n. the data have some error. So then whenever using any effective theory, like electric multiples, you choose how much accurate you want to describe your observable, okay? 30%, 10%, 1%. Let me call this alpha, and overall we should require this. So then, given the power spectrum at one loop, you can estimate the size of the two-loop term, and there are mainly two estimates that we use. This one that's useful for halos and real space, and this one that instead relies on this KR, expansion parameter. That is basically the first finger of God. And of course, we can also use simulations to test the NNLO, of course, if they are reliable. And let me just show you an example that we employed both for power spectrum, so Fourier space, and for the correlation function in real space. So the second one really is mixing a little bit Fourier modes, so it's not obvious. Now we use a slightly different method than what I described, in the sense that we look at the shift in cosmological parameters, but the idea is the same. Okay. Okay, and these are the things I consider done in the past. So now the present, okay? So let's try to go above the low-hanging fruits, and let me explain something that, me and other groups are doing now. Actually, one interesting thing, now applied to the power spectrum, and hopefully will be applied to other, to many other observables in the future, and already Uros mentioned it, okay? So it would be really nice to have now a super fast analysis to make it on a laptop. And to do that, analytical gradients are very useful, okay? So one possible solution is to emulate the theory in a smart way, and this is our own work. And also let me mention PyBird JAX, which is the latest iteration of PyBird. Also, Zvonimir's basis should be very, very fast. Not sure if it's totally differentiable, but anyway, there are other ways to do this. Okay, so this will move, cosmological analysis from the cluster to the laptop, and I think this is nice. Okay, so here it's agreement between PyBird and our emulator. We were able to use these nuts, and also we used the microcanonical Monte Carlo. That's very nice. Okay, then in the present, beyond the two-point function, the one loop by spectrum in large-scale structure. So lots of work. Bias tracers up to fourth order, redshift distortion up to fourth order, counter terms up to second order, an efficient way of computing loop integrals, and also generalization to non-Gaussian initial condition. So we did this in 3 works. At the same time, there were works by the East Coast group, and much more recently also a full confirmation of operators and redshift space distortion with also some discussion about the short noise terms, and a new basis by Thomas and collaborators. So the theory model, really now, for the power spectrum, we had 4 biases, which really on the data were 3. I mean, we could fix 1. And the problem is that now you have 11. And the counter terms and stochastic that for the power spectrum were 6, and really again you could fix 1 or 2. Now it's 13. Okay. Here there are so many that it's not super clear what you can fix, but I mean I guess that yeah, some study should go on in that direction. The problem, why did I put this in the present and not in the past, that observational effects are not fully under control. In particular, this convolution with the survey window was approximate, is still approximate. We did a binning effect only on the linear part because loop terms are small. We checked that on both the effect of these approximations are small, okay? But this will all be important for Daisy and Euclid, okay? So that's work to do on this. So here, just let me show that what I just said is okay. I mean, there is no theoretical error on simulations. And here you can look at the best fits. We did P0, P2, so the 2 multiples, the monopole by spectrum, and the quadruple at 3 level. Why the quadruple at 3 level? Again, because the window is mixing the scale, so we found that we couldn't use the loop here. And the results were really pretty nice. We found improvement of 13% on omega m, 18% on H, and 30% on sigma 8, all in agreement with Planck. So a nice thing that we write in the paper is that, I mean, these things seem small, but look, 30% is like 1/3. If you think of measuring something and you think that the error scales with 1 square root of the data, this 30% amounts to doubling the data, okay? And given that Euclid cost $1 billion, I mean, if we can use the data to the maximum, yeah, the European taxpayers should thank us, right? Okay. And also with primordial non-Gaussianity. Now, when I talk about primordial non-Gaussianity, I do not mean only local, okay? Because there is a single field non-Gaussianity, which must be there at some level, although, well, I mean, it could be much smaller than 1, but still that is information. So we should do a very good job to measure this. We found no evidence of primordial non-Gaussianity, but interestingly enough, look, for orthogonal, we are better than WMAP, okay? So, I mean, okay. So if this paper were out 10 years before, like this would be like the best in the world, eh? So, now, in the sense that large-scale structure is can be interesting for this. Okay. So finally, about present works, let me come to our last work that should appear any day now. There is not only spectroscopy in the sky. Photometric surveys will also be important now. And we can actually try to apply the effective theory also to these. Why not? In fact, there is a DS per Daisy 2 times 2-point analysis that had very nice results. There are a lot of peculiarities in weak lensing with respect to galactic clustering. There are some things like the baryonic effects and the intrinsic alignment that can be dealt with within the effective theory. There are systematics that are observational systematics that we can do nothing about, and we just follow the collaboration. Now, the main practical challenge here is to be able to determine the scale cuts, okay? And also to keep the number of free parameters under control. So this is the main drawback of using perturbative theory for weak lensing. So you see, like before we had to stop here, and now you have to convolve these with kernels and Bessel function to get the angular projected correlation function within the INJR redshift bins, okay? Now, modeling choices quickly. So in general, we try to be careful and do not use unwarranted approximation. So, for instance, we use an equal time power spectrum at linear level. Loop level is very small, and so we respect to the error bar, of course, and so we could use a Limber approximation, so equal time power spectrum. Here, in principle, you can improve. It's a bit of pain, but you can improve. Also, RSD and magnification terms are linear, and they are also computed in Limber approximation. So basically, you see, the modeling, it's the modeling we just did, and because redshift space distortion are very small, you only get one counter term. The important stuff is that these counter terms depend on the redshift, and within effective theory, you do not know their dependence, okay? Okay, I'll come back to this. Let me briefly talk about the intrinsic alignment. You see, there is this annoying fact that, you see, you measure shear from the distribution of ellipticity, but the distribution of ellipticity is not totally random because, of course, galaxy formation, tidal field during galaxy formation informs it. And so in the end, basically, there is this intrinsic alignment term such that you have to add something to the observed shear field. And this can be computed in the effective theory, and in fact, it has. The collaboration now uses the stat model. We use the simpler NLA model that Uroš also talked about, that the collaboration used in year one, okay? This we found was enough also for year three. And let me come back to the integral over the unknown bias function. So the way to solve this is not to model the bias function, but to recognize that you can treat them as a constant within the redshift bins, within the integrals. You take them away, but you use one constant for each ij combination, okay? And the problem is that now you have as many as there are bins, redshift bin combination. So you want to reduce their impact. And the way we do this is statistically at the level of the likelihood. We correlate them because their time dependence is smooth and it is of order Hubble. So basically what we do, we look at the difference of Gaussians, and then we correlate this actually with the conservative choice. And so our prior is like a multivariate Gaussian with a non-trivial covariance, okay? Very good. And finally, the scale cuts. Again, we have the NNLO, but we also have a way to estimate that comes from the UV sensitivity. So I showed this because it's cool. Pierre made it like super cool. So this is, the red one is basically the impact of the UV part of the power spectrum in the projection integral, okay? And the dashed one is when you substitute to the power spectrum in the projection integral this NNLO estimate, okay? I mean, these lines are basically functional derivative of the projection integral with respect to P of K. So yeah, like you take a slice of K and you move this. So in practice, the red line is the integral of all of this. As you see, I mean, at some point we have to stop. So this is for shear. We did the same thing for all the 3 times 2 PT. This shear minus combination, we basically can barely model. The shear plus, we can model a bit more. How much more with respect to the collaboration? Well, we cut more. We cut the gray lines. This is the lens, so galaxy-galaxy autocorrelation. Collaboration cuts at the dashed lines. We cut the gray. This is the galaxy shear collaboration. So we cut less only in these bins that do have a very large error bars, because those are the bins in which most of the sources are closer to us than the lenses. So I mean, these bins basically they have a larger error bar, and therefore to us it seems that we can model them up to smaller scales. And for shear, in fact, we do cut a lot more, okay? The reason why for shear we cut a lot more is that the effective theory for matter is good, it works, but for matter we do have a UV theory, which is called the Vlasov equation, and which is solved by embodied simulation. And so if you use that, then, I mean, you could, in principle, go to smaller scales, okay? But anyway, we keep the model consistent such that, I mean, this goes into galaxy lensing, and there you cannot use halo fit, at least in a simple way. Let me stress that lensing has larger error bars, but the interesting thing is that H0 in lensing is measured independently, because instead of BAO, this comes from the amplitude dependence that involves K equality. So in fact, you can estimate this, and you see, you can estimate, convolving with the projection kernel, the degeneracy in this omega m H plane. And in fact, we seem to agree with what the results are. And so these are the flagship results for us. So the yellow is the collaboration, the blue is us, okay? So we have, of course, larger errors, and this is the price to pay for more parameters and different scale cuts. But we do agree better with Planck and Boss, especially in this omega m H plane. And there is reasonable precision on omega m S8. We are not competitive on small h, so H0, but the H0 measurement is independent than the BO. So it is still interesting, I think, to look at it, okay? So summarize the standing part. Where do we stand? Power spectrum over loop, I think it's totally settled, okay? So you can also use a full effective theory pipeline, okay? Self-consistent determination of K-max, analytical covariance. You may not mention a simulation at all, which makes Leonardo very happy. Then we also kind of understand the prior on biases. I will have something to say in a moment. The best spectrum and one loop almost done. So one loop expression, It's been calculated twice, efficient implementation done twice and independently. K-max determination, we mostly agree. Also the study of IR summation that was a bit uncertain, now I think is on solid ground. Not an official analysis yet, because there are these two things missing. I mean, this is much more important than the second, but having also a full analytical covariance would help, because you know, you can get a large number of triangles, and so you need to have a large number of mocks. Still, you can do compression, for instance, using Oliver's method, but I mean, this would be nice, okay? So this is not an official analysis yet, but soon will be. And the 3x2 point progress analysis is in progress, I would say. So here I talked to you about the main difficulties from the data side. From the theory side, we, I mean, could think of maybe joining this with HaloFit, with the UV. And the issue is, of course, with these projection integrals, does the new physics show up at all? Which new physics is best looked at using photometry? And, okay. Very good. And the future. So towards the end. So let me repropose this thing about the priors, okay? So there is a lot of discussion about the priors on these EFT parameters, and I fear that this is more important now for the bispectrum and also the lensing. You see, there are people who still do not like the priors that we put on EFT parameters. We know that they are perturbative correction, so we only know that they have sigma equal 2. 2 means that it's of order B1 for us, really. Now, other choices are possible, but for instance, in these works, it's shown that the best fits are the same because the parameterization is the same. And as you saw from the PT challenge, at least for the power spectrum, if data are precise enough, we do agree, okay? The problem is that the credible intervals can shift due to projection, and there is the decade-old question: what should you put in the abstract on your paper? So I measured omega m to be what? Like, what do I get as a number? And usually in Bayesian analysis, we take an expectation value with this measure being the Lebesgue measure, like 1. If the data are not precise enough, if the posterior on the parameters is not Gaussian, you are guaranteed to have a large projection effect. So basically, your 1D that should be here, the best fit is here, you find it there, okay? So what we decided to do, and you are doing a morally wrong thing according to some very famous cosmologist, we do adjust the prior. Basically, this is nothing but an approximation to the Jeffreys prior. In fact, in the analytically marginalized subspace, we do take a Jeffreys prior, and we do this for both for the bispectrum and for the power spectrum. So here I show a table that the projection effect, that is the deviation from the best fit on the single parameters, is nullified with this prior. So yeah, this is the way that we chose. Now, what to do in general, okay? Well, you can say just wait. I'm not sure waiting is good enough. So perturbativity prior is a choice. Well, it's actually kind of an obligatory choice, meaning that you have a perturbative theory, your model is really not reliable in some corners of parameter space. And in fact, there is this perturbative prior, which actually is more than just loop is smaller than linear. It is loop should be of order the loop. So this forces the loop to be much smaller than linear at very large scales. So we implemented this, and the shift chi-square is like negligible, but the shift, the improvement in error bars is interesting. The other thing is something that I think that the EFT could get becoming older and wiser. So you can get some controlled UV information. So sometimes we use some old fitting formulas, this coevolution from simulations. As a first step, you could fit the HOD. So add the small scale information in the form of HOD, so something approximate. We did this, you see, I mean, and in fact, the projection effects are sensibly reduced. So both us and the group of Misha has worked on this. In fact, Misha has been even more aggressive in the information that he put, and I mean, that is fine. Another interesting and more general direction is this hybrid SBI by Oliver and Chirac, such that you try to really, I mean, make friends with the machine in the sense that you try to get reliable small-scale simulation, not having to worry about the large-scale environment that is given to you by perturbation theory. This, I think, is probably a direction that is worth exploring. Now, of course, yeah, to me, that I'm now a very old person, I mean, I don't know, can we claim that action on new physics based on small-scale information, or mainly based on small-scale information? To some cosmologists, the answer is yes. I always a bit cautious on this, okay? Okay, let me now discuss, you know, for the future, okay? So technically, where do we go with effective theory? Higher loops, well, two-loop power spectrum will be done soon, okay? Integrals are complicated, but not an issue really. So determination of Kmax is easy. Will it be useful? Maybe, depending on the tracer, on the data noise, it can be. Also, we could construct these p/slash variables that we did, or Q0, or the EOS Cauchy-Marro, and we can practically reach 0.5, sorry, no dimension, but inverse megaparsec in Kmax, for instance. It could be useful for weak lensing, okay? Then, another direction, obvious technical direction, is higher point function or field level. So, in principle, today, you could include up to the 3-level 5-point function, though there you have additional 4 biases. But at least the 3-level trispectrum has no more biases, no more uncertainty than the 1-loop bispectrum. Why don't we put it? The problem is that the measurement analysis seem daunting. On the other hand, if you think about the field level modeling things at the level of the map, I mean, the map is there, the catalog is there, you just smooth a map. So the measurement and the model are simple. Now, how about the likelihood? We have a nice forward model with Dennis, but I mean, there are also many forward models. The problem is that now when you start thinking about the likelihood for bias tracers, there's been a talk by Kazu that the noise could be a serious problem, and you may not end up making the full inference. However, let me say that the forward model is super useful to help with standard analysis and also with the perturbative-based, you know, right? You make a billion mocks, you train things on that, you check the covariance, you check the window application. I mean, it's useful to be able to have a fast perturbative forward model at field level. And then finally, why do we do all this? To get new physics. Now, lambda CDM is very well studied and also boring. So this today is really cosmologies before LHC moment. We know, for instance, that some new physics is there. In particular, for us, the neutrinos, okay? They exist, they are light. We must measure their mass. At the moment, we have surprises in terms of, I'm referring to the DESI results. So the likelihood is shifted too much towards 0, the posterior. So we do expect to get this, and maybe we get surprises, which are not a bad thing. Also, again, the inflationary dynamics is not free fields. It may be really almost free fields. Still, we need to push for primordial non-Gaussianities, not only local but single field. And also, there's a bunch of under the lamppost physics. Let me mention dynamical dark energy, okay? It may or may not exist. Let me remind you that non-scalar field models solve the CC problem. So, you know, it's not why you do it. You just do it to search for things that we know existed at some point in the universe. You know, at some point, the inflationary almost this interface ended, okay? Maybe it happened today too, okay? So, however, we must go beyond the W0, WA, I believe. I mean, it's useful these to point in some direction, but at this moment it causes more confusion than anything. Cold dark matter, it's not only billiard balls. I mean, so this is a useful approximation for M-body, but here, can LSS help? It's a question of scales and naturalness, of course, if you try to build a model. It is an exquisite probe, large-scale structure for ultralights, and I mean, the organizers have done a lot of work, in fact, trying to bridge these two worlds. But then, yeah. -5. I'm almost done. I'm literally done. Okay. So, so can we, however, just claim that there is something beyond? Okay, something is rotten in the state of new lambda CDM. Let me put new because neutrinos are real. So you see, this is the first time that we can use precise data at vastly different times and almost complementary length scales. So CMB, LSS, also supernovae, Lyman alpha, what else in the future? So literally now we are making, you know, the constraint on a model being more and more rigid. Like, for instance, now the constraint on omega k, because you have a small redshift distance, no, becomes more precise when comparing to large distance. So as for perturbation, we want to be able to expose anomalies and tension. Of course, you always need some parameterization. One parameterization that, I mean, let me mention is this large-scale structure bootstrap. So you are more agnostic than lambda CDM and biasing. So you impose just symmetries and parameterize the kernel with basic building blocks. Of course, you can match to specific models. The idea is then you measure these coefficients yeah, hopefully you will be able to measure them. Another thing that actually makes me very, very curious is can we use machine learning, literally agnostic parameterization? And I just cited this paper applied in particle physics, where F is just an approximate of the number counts, and then you build a statistics by training it on a noise, so that at the end, when you apply it to data, you ask the machine, is it different than what you have seen before that is just a standard model? And the machine can tell you, oh, this is different at 5 sigma. And you say, let me look at the best fit. So where does it deviate? And then you may discover some new physics, hopefully. Okay. So is this the end of the beginning of the end? Let me just summarize what I've been trying to cobble up. So the effective theory has been successful. It stays strong in the wake of AI, I would argue. So the one loop power spectrum, one loop by spectrum, 3 times 2 PT, they are all things that have been done. What is next for the theory? Maybe more technical developments, other observables, and we'll hear Matteo talk about Lyman alpha, for instance. Again, should we become friends with a machine? Possibly, you know, the best of both worlds, as long as they are reliable. I think it is a way to get more precise constraints. And also, I mean, yeah, getting new physics, I mean, known unknowns we should look for and try to get smarter to look for them. But in the meantime, we should also, I think, be able to expose anomalies and tensions, and especially because, you know, it's very hard already to model lambda CDM. So now you invent 1 million models to look for. It can be, you know, you may not learn what you thought you would learn. And so maybe a way to go is a more model agnostic assessment, whether there is new physics or not. Right? Thank you. Yes. Yes. So, so it's very simple. So you have the multiples, or actually mu dependent power spectrum with redshift space distortion. Is just that you can build a linear combination of data that is not sensitive to mu, and so it's yes. Yeah, so the first one who invented it was Roman, 2004 or something, yes. Then, yeah, the Ushkus group used this and called it Q0. It's not independent of mu. It minimizes, well, actually, the way we did it with this P slash, we minimize the NNLO term. So we minimize the effect of the finger to God, okay, with the linear combination of data that that we have. But basically these, and also if you do what's called the first wedge, so instead of multiple, you integrate the mu, they are all correlated at like 95%. I mean, these variables are there, and they are basically allow you to get an extended Kmax, which improves a bit omega m. Yes. Yeah. Yes. Yes. You mean this? Sorry. This. Yeah, no, this is actually just the linear power spectrum, and this is like the transfer function, like BBKS or whatever approximation is. So basically, so the idea is this. Of course, you. No, not for these scales. No. It's basically the amplitude of the lensing signal, which smooths out the BO. So that's the only handle on H0 you have, right? Because you see, I mean, these are all dimensionless observable. With dimensionless observable, you are never able to measure a dimension full quantity unless, well, it comes from a scale. So, and the scale here is K quality, ratio with K quality. Yeah. Yes. Okay. No, Limber only for the loop. So linear, unequal time, plus loop, we approximate the integral. No, so no, the full sky, we do flat sky always, and by flat sky I mean I take the limit of the Wigner matrix that becomes the cell, and then Limber is another thing that. So here, no? So this is not beyond. This is already flat sky. What I call flat sky is this. Otherwise, this would be a sum, right, over discrete L with the Wigner matrix, okay? So this is a flat sky. And I mean, 250 arc minutes is the largest, so it's okay to do this, right? I mean, I checked, yeah, that the sum and the integral there give you the same thing. Then Limber is this, for instance. Yeah, maybe that's why you were confused. Okay, sorry, yes. So here we do unequal time for the linear. The loop then is calculated in Limber, okay? Because it's smaller. Here we use Limber right away because the errors are so large. Yes. Yes. No, you're right. Yeah, of course. Yeah. No, sorry for not citing you. Yes, I should have said that. Yes. Sorry. Why we cannot? Yeah, because it's hard. I mean, yeah, we could use. Okay, yes, yeah. This. So we could use your estimator. Yes, that is true. We actually tried back then, and we were having a bit funny results. But you know, maybe we didn't understand fully. Yes, but yeah, let me mention that yeah, Oliver has an estimator which undoes the effects of the window. Well, I mean, yeah. Okay. Okay. Very good. Yes. 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 So when I say we put the baryonic effects, I mean this means the following: instead of so this delta is actually the adiabatic, the total matter field. So it's omega b delta b plus omega c delta c. Okay. Then there is the isocurvature one, and they are coupled by gradients. So we put the first correction of those, okay? We put those in galaxy and galaxy lensing, and we find that they are small. For shear, they are really tiny at our scales, at the scales that we fit, right? And for galaxy and galaxy lensing, the cross one is actually, you know, it improves a little bit the fit, yes.